All right, guys. Well, this is it. This is the last one. We're going to talk about the divergence theorem, which is also referred to as Gauss's theorem. Okay. Now, if you think about it, what did we do? We had a whole bunch of theorems. We had Stokes's, we had Green's, we had all kinds of theorems to help us deal with line integrals in different sort of spatial contexts. What divergence does is it gives us a tool to evaluate flux integrals. Okay? Remember, this is just flux integral. This is the form. All right? But what it says is, well, let's hold on. We got to preempt that little diatribe that I was about to launch into. First things first. We know that E is a simple solid region with a boundary surface. And I'll give you an example here in just a sec, just like I did before. That S is a given positive orientation. It doesn't matter what the orientation is, but we choose outward. We got to stay consistent. Let's put it that way. And we've got F, which is a vector field where we have continuous partial derivatives in R3. Okay, easy enough. Now watch what divergence theorem says. And again, I'm not going to do any examples. I'm just going to give you the theory. That's all I care about because we can do examples in class. Again, just like Stokes' theorem, there's not a lot of them and they're not terribly difficult. But I do want you to understand the theory behind this. Okay? What it says is the flux integral is equal to, so just remember what a flux integral was. You got a vector field here. You've got this ds where s is a vector as well. You take double integral over the surface and you get the flux. And we never really defined necessarily what flux was. Not in a we just called it the flux integral, right? When we had the surface integral, we called it flux. Now we get to actually define what it is, sort of in real time, as it were. According to the divergence theorem, it says it's the triple integral over the surface of the divergence of f dv. Now, we're not afraid of dv. We've seen it before. But what does this mean? What does this guy mean? It means we're summing all of the divergence over the surface of this solid region. Okay? That's what this triple integral means, right? Add a whole bunch of stuff up. But like, think of that sort of contextually. Again, let's keep it simple. Let's say that I've got a hemisphere, right? Like this, and this hemisphere is sitting in a vector field. Now, you're probably already sort of thinking, well, let's think along the lines of water or something akin to that, all right? And I've got some crazy vector field that's doing, I don't know, crazy stuff. I got this nice positive orientation, right? Stuff's coming out all over the place, okay? Now, I'm going to try and relate, we'll see how successful I am. I'm going to try and relate the flux integral to this divergence. If I sum up, remembering what divergence is, right? It's the tendency of something to want to get away from its source, as it were. If it's negative, it means it runs, think of it like a current, or an easy way to think about it is like a hose at the top of a slip and slide. Initially, you've got a great deal of divergence, don't you? But as the water moves down slope, it sort of reaches maximum velocity and it decreases. Okay, but in the case that I've just drawn for you, and I'll show you a way better picture here in just a sec, is if I sum all of the divergence up over the entire surface, I reckon I should probably stick some downward guys off the bottom, right? If I add all of that divergence up over the entire surface, then that is equal to flux. That's what flux is. That's what a flux integral is. It's the total of all the divergence across the surface, as opposed to what we've done with flux integrals in the past. Now, I'm going to pop away for a second. I'm going to give you a much better look at a solid that's submerged. Again, I'm always thinking in terms of fluids. Apparently I should have been a hydrologist. That's, say, dropped into a vector field. Okay, so I'll see you back here in just a sec, and I'll show you a really cool. Little graph. Okay, so this is a much better representation of what's going on. So let's take a gander at this thing. This ball is E, all right? All of these black vectors in this context represent F, what's going on as far as the vector field that this ball is interacting with. Now, what we're doing is, according to the divergence theorem, what we're doing is we're simply summing up the divergence of these vectors. Because remember, when I take the divergence of F, this guy right here, it's a scalar, right? It spits out scalars. So these can't be measures of the divergence. The divergence comes out of, like, what does that little vector right there at that point do? What is its divergence? How about this guy? How about this little vector right here? What is its divergence? Well, the divergence theorem tells us to add up all of the divergences of all of those vectors, and that will equal the surface integral or the flux integral of the entire surface, all right, when I take that surface integral. Whoa, that's mind-blowing, isn't it? That's crazy. The cool thing about the divergence theorem is we go from vector calculus to just our regular multivariable triple integrals. So it may be way easier to define an integral, like, for example, a sphere, right? I can do this thing super easily with spherical coordinates. Take the divergence of that, use that to define my limits, take the divergence of my vector field, and I'm off to the races. It's a piece of cake. However, maybe it's not so pretty. Maybe I actually want to take this, this flux integral, where I just take f and I dot it with the cross product of the vectors, which we've done a bunch of times in the past. All right, so again, I've said it before, it works like a hammer. You get to use it however you want, whichever way is easier, or of course, whichever way I tell you to do. Okay, now again, no examples. We'll do examples in, whoa, I don't know what that was. We'll do examples in class tomorrow. And guys, that's it. You made it. So excited. So I hope you enjoyed it. It's been a wild ride. So I'll talk to you guys tomorrow.